of this course on web data mining. We were on chapter 2 last time. Today we're going to try and finish this chapter. If you recall from last time, we discussed the basic indexing pipeline, which is shown here. We discussed how to convert the documents that need to be indexed into a sequence of characters, and then how to tokenize this character sequence. And we also started looking at some ways to normalize those tokens which are generated by the tokenizer. Today we're going to look at the linguistic module or normalization in more detail. So this is done, and we also discussed tokenization. We're going to discuss linguistic pre-processing today, and we're also going to look at, so this is the first part of the chapter, where essentially they discuss how to generate the terms that finally go into the dictionary of the index. In the second part, we're going to look at how to speed up the postings lists using faster merges, how to speed up query processing on the postings lists using faster merges. And we're also going to extend the index we built in chapter 1 to accommodate phrase and proximity queries. So any questions from last time? I think we were on this particular slide. Are there any questions up till this point from the chapter? No questions? Okay, so let's go ahead from where we stopped last time. In the linguistic pre-processing phase, we take the tokens that have been generated by the tokenizer and we normalize them into some canonical form. And the reason for normalization is that different, if you look at a particular word, very often you may want to find documents which contain variants of that word. Even if you enter a word like say automation, you may be interested in documents that contain the word automate or automatic. So we want to somehow group together these different variants of words and collapse them into the same term in the index. So documents containing the various variants will enter the same postings list, so that if your query contains any particular variant from that set, you're going to get documents containing the other variants as well. For example, if your query is USA without the dots, documents containing USA, documents mentioning USA with the dots are also relevant to your query. So that is why we map both these tokens, or we map both these words from the original documents to the same token, so to the same term, sorry. Recall the difference between a term and a token. A token is a particular instance of a sequence of characters that is output by the tokenizer, whereas a term is what is output by the linguistic module that finally enters the dictionary of the index. So both these tokens, when normalized, will map to the same term, so that when your query contains either of the two words, you're going to get documents containing both variants. Now you can think of all the tokens which map to the same term as forming an equivalence class. So for example, USA with the dots and USA without the dots form the same equivalence class. And that equivalence class is represented by USA because this is the term that is finally indexed in the dictionary. So the periods are deleted from u.s.a and nothing is done to this token. This token remains as it is. So the normalized form of both these tokens is USA without the dots. Similarly, if you have hyphens in any of the tokens, a common way to normalize such tokens is to delete the hyphens so that anti-hyphen discriminatory and anti-discriminatory without the hyphen both map to the same term, that's anti-discriminatory. So these two tokens form an equivalence class, and this equivalence class is represented by the term standing for that class. Similarly, these two tokens form an equivalence class represented by this particular term. So that's the overall purpose of normalization. We want to be able to create these equivalence classes so that when the query contains a particular variant of a word, you're going to get documents containing the other variants as well. Now, as always, normalization is heavily language dependent. So depending on which language the documents are written in, the linguistic module that you use is going to be different. In English, for example, uh, the word resume without the accents, sorry, the word resume without the accents and the word resume, which is basically a French word, which is basically your CV or curriculum vitae, which you submit when applying for a job. These two mean different things, right? Resume means to start something after you've stopped it, and resume with the accents stands for something very different. So how do you deal with accents in normalization? That's the question. So one common approach is to just delete the accents. So both resume and resume would get mapped to the same term. Now obviously that doesn't look good for this particular example, but for other examples, like for example, cliche without the diacritics, without the accent, and with the accent, both should map to the same term. But in some languages other than English also, accents can often be used. So a word with an accent can mean something pretty different from a word without an accent, in which case it may not be a good idea to map both of them to the same term. But the most important criterion to use when deciding whether or not you want to just blindly delete accents or whether you want to delete accents in general with some exceptions, your criterion should be to examine your user base and see how the users are going to write their queries for these words. If the users are not going to use accents in the query, then there is no point in distinguishing between these two, because even if the users are interested in how to write a resume, for example, they're not going to write resume with these accents, they're going to write it like this. So in that case, there's no point in distinguishing between these two by having them as separate terms in the index, because if you do that and if the user is searching for resume, then you're still going to be entering this particular postings list for this term. In German, umlauts, which is this particular character, is often pronounced as uh, so this is Tübingen, which is which can also be written as TUE. So this U with this particular accent is pronounced as we. So you want to treat both these tokens in the same way, because somebody could write the query like this or alternately like this, or some document could mention this particular variant of the word or this particular variant. So both of these will be collapsed to the same term. So it's often standard to normalize these tokens to a de-accented term, because users may not often type the words using diacritics or accents. So all these words, all these three words would be mapped to the same term, which is this one. Other examples of normalization, we looked at some of these last time. We looked at the fact that dates can be written in different ways. Uh, the way dates are written in Europe, the way dates are written in America, the way dates can be written using these three numbers separated by slashes, or writing down the full month, March 30th, 2010, or something like that. All those different ways of writing dates need to be normalized to a single term if the date is the same. So this applies even to other languages. In some other languages like Japanese, for example, dates are written in this particular way. So they need to be mapped to the same term as dates written, the same date written in this particular way in languages like English. We also saw last time that the Japanese character set is pretty complex in that they use 4 different scripts, and a single word can be written in 4 different ways depending on which of those 4 scripts you use to write that word. So if a query is written in one particular script, we should be able to match that query with documents containing those words written in other scripts. So that's something which normalization for Japanese documents needs to take care of.
Hello, sir. I have a small doubt.
Yeah. Go ahead.
Okay, sir, how do you differentiate a mathematical term like 7 divided by 30 and a date 7/30? So even that would be a confusion. So how do you
Yes,
differentiate
yes,
them?
definitely. That's true. Um, so it would depend more on what users tend to mostly mean when they type that, or what documents tend to mostly say when you. I mean, if you have a document that is clearly a mathematical document, for example, you could treat it differently. I mean, that's one sophisticated way to do it. I'm not sure what Google does, but if you just type something like this, so Google is interpreting it as, you can see that it's giving you the result, interpreting it as a mathematical operation, but you can also see that it's treating it as time. No, is this time or something else? So it's treating it as 7-30 also. Um, so you can see that the list of results that are returned contain different meanings for this particular query. It contains the mathematical operation as well as other possible meanings. So here is an example of the date, 7/30/09. So basically you are being returned both results over here. So it's because it may be just impossible to differentiate, what exactly you mean when you write this. Some people could probably interpret it as um, the mathematical operation of division. Others could interpret it as a date. Others could interpret it as, some other meaning. Likewise, in German, for example, when dealing with documents written in other languages, many times people may be using particular quotations from other languages within that document. For example, a German sentence could refer to the university MIT, but MIT is also a German word. So then the question is, is this the English word MIT standing for the acronym MIT standing for the university in the US, or is it a German word? So you may need to use some sophisticated language detection techniques to do this, if at all it's possible to make out. And as always, it's important to emphasize that the same normalization and the same tokenization needs to be done on both the documents and the query terms for this to be effective. Other examples of normalization in English are case folding, something we saw in the very first lecture where we had these friends, Romans, and countrymen, the tokens being converted into their lowercase forms. So one approach to normalization, one approach to case folding within normalization is to simply reduce all letters to a lowercase. And that will allow you to do the following. If the query is automobile with a small a, and if there's a document which has a sentence that starts with automobile, so that sentence would have the A capitalized because this is the first word of that sentence. So you want this document to be considered relevant for this particular query. So that's why you may think of reducing all letters to a lowercase. But there will be some exceptions. For example, if in the middle of a sentence you have words being capitalized, words appearing in a capitalized form. So for example, if this company General Motors appears somewhere in the middle of a sentence, because it's a proper noun, it will be capitalized. In that case, you may want to treat it specially because proper nouns usually appear capitalized. And if a particular word appears capitalized in the middle of a sentence, it's a hint that it may be a proper noun or an acronym or the name of an organization. In that case, you may not want to do case folding because you want to keep proper nouns as they are. Clearly, General Motors shouldn't be uh, this word general here and this word motors here does not mean what the words general and motors in separately taken mean in the English language. But again, you have to look at what your users are going to use. If users are not going to capitalize, then there's no point in your desisting from case folding. If users are not going to capitalize, there's no point in treating capitalized letters separately. It's best to just reduce all letters to the lowercase. Here's an example where let's take this query c.a.t. This stands for this company Caterpillar Incorporated. And even today I was just checking, if you enter this query on Google, you see that the first result is on uh, what is it, on cat products and services. It is some company, I guess, but there's also this result on cats, the animal. So what's happening is during normalization, this c.a.t, again with the periods deleted and with the capitalization removed, is getting mapped to the what the animal cat would have gotten mapped to, and so the results are kind of mixed. So this what we've seen so far is one particular approach to normalization where you create these equivalence classes. You create these equivalence classes and you take all the variants or all the tokens belonging to the same equivalence class and you map them to the same term. You modify those tokens to the same term. An alternative way to do normalization is not to do equivalence classing, but to do what is called query expansion. So in this particular way of normalization, what you will do is you will take every token that the tokenizer emits and you will add it as it is as a separate term in the index of in the dictionary of the index. So you don't do any normalization, you just add those terms, add those tokens as separate terms in the dictionary. But when processing queries, you will do something called query expansion. So just to take an example, let's go back and so let's say we consider these two tokens u.s.a and USA. So both of these would be separate terms in the dictionary. So when a query like USA comes, you'll do query expansion. So you will have another, you can think of this as a hash table of some sort, You'll take the query and you'll look up that particular word in the query in the hash table, and what this will tell you is it'll give you um, a list of words which conceptually would have gotten mapped to this particular word had there been normalization, had there been equivalence classing. Right? So instead of collapsing u.s.a and USA into the same term, another way to implement pretty much the same result is to take the query and then expand it into USA or u.s.a. So if I'm searching for USA, my query will be expanded into u.s.a or USA. That means the postings list that will be looked up will be both u.s.a and USA. So based on what this query is expanded into, we'll take this list of uh, terms that this query is expanded into, look up each term in the dictionary and take the OR of the postings list of all those terms. So this is called query expansion, and the advantage of this, here's an example where you can do something with this that you could not do with equivalence classing, and that is asymmetric expansion. Suppose a user enters the word Windows into a search engine where W is capitalized. So the user has deliberately capitalized W and written the other letters in lowercase. Now, it's very likely that this user is searching for the Windows operating system. In that case, you will take this query and you will look up only the same variant Windows in the dictionary. So you will take this query and look it up as it is in the dictionary and retrieve the postings list and return the documents to the user. But if the user had entered Windows in small letters, it's possible that the user could have been looking for the Windows operating system. It's possible that the user could be looking out for window repair in some way, or buying windows for his or her new home. So Windows could mean either of those two meanings. In fact, it could, if it refers to the glass, the glass windows, then even a document containing the word window in singular form would be relevant. Whereas a document containing the word window in singular form would not be relevant here if the user was looking for the operating system. So if this is the query, it will be expanded into these three terms: Windows or Windows with a small w or window. Because either of these three terms could be what the intent of the user was when the user typed in this query. And if the user types in just window, then clearly it's probably not a person who's looking for the operating system, which is Windows. So you'll look up only the postings list for window and Windows, not the operating system. So if we had equivalence classed these three terms, then they would have been treated in the same way. But if we do query expansion, we can treat these three terms in different ways. If this is the query, we can expand it like this. If this is the query, we can expand it like this. And if this is the query, we can expand it in a third different way. So this is, this gives you more functionality, but it's less efficient in that, uh, firstly, you will create a lot more postings lists, right? If you don't do equivalence classing, but if you do query expansion, then the number of postings in your dictionary is going to go up. Why is that? Because if a particular document contained, let's say, window and Windows, both, referred to the window in the singular and in the plural, there would be two separate postings, right? One in the window posting list and another in the Windows postings list. But if we equivalence class these three variants, then there'll be only one posting for that document. So the number of postings is going to go up. So it's less efficient in terms of space, but it's more powerful because it allows you to do this asymmetric expansion. Now during normalization, we may also want to handle synonyms. That is, if the query contains a particular word, we may want to also retrieve documents containing synonyms of that word. For example, if the query is car, then we may want to retrieve documents containing the word automobile, but even if it doesn't contain the word car, and vice versa. If the query contains the word color written in this particular way, American style, you may want to retrieve a document referring to color with this particular spelling with U inserted, the British style. So, so we can create a list of synonyms by hand, and we can equivalence class those synonyms so that the different synonyms will map to the same term in the dictionary. And then uh, we can rewrite the query. So once we do this for the document, when the query comes, we can rewrite the query to map to either some canonical synonym which we choose as the term, or we can just um, we can. So one thing that I want to mention here is that it doesn't really matter what the term is, what the actual string comprising the term is, as long as all the different tokens map to it, right? For example, i could I could say that both the word car and automobile map to the same term, but that term is going to be car. This is one option. Another possibility is I could choose the term to be automobile. It doesn't matter, right? The results are going to be the same. It doesn't matter which of these two I choose as a term. In fact, it doesn't matter even if I choose some XYZW string. It doesn't matter what this particular string making up the term is, because what really matters is what are the tokens that are mapping to this term. The actual value of this term need not even be a valid word. It can just be some you know uh, some string in an entirely different character set. What's important is this mapping, the equivalence class. So we can rewrite a particular token, say automobile, as car dash automobile, right? So another possibility is I could write this term as car dash automobile. So this is how we can handle synonyms. We can do equivalence classing, or again we can do query expansion. So when we get a query like automobile, we can transform it into a query like automobile or car, which means we'll look up the postings list for automobile as well as the postings list for car and then take the union. So synonyms are different words that mean the same thing. Homonyms, on the other hand, are instances of the same term but with different meanings. Right? So this is different words, same meaning. Homonym is the same word but different meaning. For example, the fruit blackberry and the phone BlackBerry, these are homonyms. Of course, you can say this B is capitalized, so if the user is entering BlackBerry with a capitalized B, it's likely that the user is searching for the phone. But other examples are, say, Jaguar. If the user just enters Jaguar, it's not clear whether it's Jaguar the animal or Jaguar the car or Jaguar the operating system. And if you look up on Google, you just search for Jaguar, you get all the meanings. You get Jaguar the car, uh, You get some results for the animal jaguar. And there are some other meanings as well. So you can see that this single word, this is jaguar the cat, and this is jaguar cars. So and there will be some other results for the jaguar operating system. So you can see that the results are mixed, and that makes sense, because if you just look at the word jaguar, it's not clear from the word itself what the user had in mind. Some people could have had the car in mind, others could have had the animal in mind. So how do you deal with homonyms? Um, you can basically create a single postings list for the homonym. Of course, if the user enters jaguar animal, then you'll take the jaguar postings list, intersect it with the animal postings list, and that will filter filter out the documents from the jaguar postings list which did not refer to the animal. How do we deal with spelling mistakes? Well, this is particularly a problem with names. For example, a name like Chebyshev, if you've done a course on probability or stochastic processes, you may have done Chebyshev's inequality. Okay, I don't remember how uh, Chebyshev is spelled in Russian, but there are variants of this spelling. Um, I don't know. You can probably think of many other names where um, some people may write it in one particular way, others may write it in another particular way. But when pronouncing it, it will sound the same. So one approach to we're actually going to see how to build a spelling corrector in the next chapter. But one particular way to deal with spelling mistakes is in the normalization phase itself, where we use something called SoundX. SoundX is an algorithm which was developed particularly for names. And what we do is what the algorithm does is it takes words that sound similar and groups them into the same equivalence class. So both these words would be normalized to the same term, because it's going to look at the pronunciation and it's going to generate a string based on the how you're pronouncing this word. And based on the pronunciation, it's going to group words into terms. So that means if the query is written in one particular spelling, you will be able to retrieve documents containing the other spellings as well. And we'll look at SoundX in more detail in the next chapter, as well as other techniques for spelling correction. So are there any questions so far?
No, sir.
Okay. So let's look at something called lemmatization. This is a sophisticated natural language processing technique for normalization. In the English language, words like am, are, is are all derived words from a base form or a stem form or a root form called be. Right? If be is written in the present tense, it's am. If it's written in the past tense, it could be was. So what lemmatization does is it collapses tokens into terms based on a sophisticated linguistic technique that will map the various words that are derived forms of this base word into the same equivalence class. So car, cars, 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 all of these would get mapped to the word car, because car is the root form of this noun and be is the root form of this verb. So derived forms, all the derived forms will get mapped to the same equivalence class or to the same term, which is the root form. So lemmatization reduces the various derived or variant forms to the base form, and it creates this equivalence class of all the variant forms. So if the document had this particular sentence, the boys' cars are different colors. After lemmatization, the tokens would be, assuming that each of these words is a separate token, it would get converted into the boy. So boys has been converted to boy. Cars becomes car. So plurals are converted into singular, for example, because the root form will be in singular. R gets converted into B. Different remains as it is, and colors is again converted into the singular form. So the word lemmatization derives from the word lemma, which refers to the root form of a particular word. So it's the dictionary headword form or the root form of a particular word, of which all the variants are derived forms. So lemmatization is taking all the words and mapping them to the root form or to the lemma.
Does this happen to the entire document, this lemmatization?
Yeah, so this is again part of the linguistic module. So what's happening is that if the document had this particular sentence, tokenization would split this sentence along white spaces. We are assuming a simple tokenizer here. So assume that every word is a token in its own right. And after tokenization, each of these words would get normalized. And if lemmatization is the way we do normalization, then each of these words gets converted into its dictionary headword form or its lemma form or its root form or base form, which is what this sequence of words is. Each word here is the root form of the corresponding word in the token stream before normalization. This is after normalization. So these words would be then indexed. These would become the terms. Is that clear?
So, like, what order does this happen? Like, in the last one, we saw that cat and cats were brought down to the same thing. It could have been the cat, like CAT exam as well. And here we're again bringing it down to some other thing. What exactly happens? Which schemes are implemented here?
So what I'm explaining to you here is a variety of schemes. Now you could implement some combination of them, right? So lemmatization, for example, is referring to proper words that you find in the dictionary. Whereas, acronyms like this, these are proper nouns. So proper nouns could be treated in a different way, right? So the cat exam and this company cat, you could normalize these by converting them all into lowercase. Right? So lemmatization is particularly about actual words in the language. Proper nouns are not actual words. Proper nouns,
Separate tokens are getting converted.
it's the separate tokens. So this is the
Okay.
sentence. Think of these as a token stream. Okay, let's imagine.
Okay.
I'm
Okay.
putting commas here to indicate that this is a sequence of tokens which will be generated from an original sentence. And then this sequence of tokens gets converted into this particular sequence. So basically, this word gets normalized to this word gets normalized to this root form, and so on. Right, so this
Okay.
is one normalized token, this is another one, this is another one, this is another one.
So
Yeah.
it nothing happens to the documents as such, right?
Yeah,
Like they are not.
the documents will remain as they are. You're parsing the documents and then generating the tokens.
Okay. Thank
And
you.
then
Yeah.
you're parsing those tokens, and each token that you're generating is getting passed through a lemmatizer, which will convert that token into the normal form. So it's just like, this is the phase we are talking about. So this is what I showed. Okay, the sentence that I showed was a sequence of tokens, which means we are at this stage, and that sequence gets converted into a sequence of modified tokens, which is the normalized form. And we are looking at a particular technique called lemmatization, which is used to convert words in a language into the root form. Now, obviously, that doesn't apply to proper nouns, right? It doesn't apply to proper nouns like CAT, the company, or General Motors. Doesn't apply. I mean, these are not proper words in the language. These are names. These are proper nouns. So you'll need to normalize them in a different way. And lemmatization is just one of the techniques. I mean, there are other techniques. I'm just going to talk about something called stemming, which is another way to do this kind of reduction, where you reduce terms to some root form. Okay, so we are discussing a bunch of techniques, and you may want to choose a combination of these for your particular use case. Right? We discussed some of our examples were from other languages. So if you're not going to be using if you're going to be using the English language, then those won't be relevant. But still, you'll need to deal with diacritics. You'll need to deal with heterogeneous documents where there are terms from other languages. You'll need to deal with synonyms and homonyms. And we discussed equivalence classing as well as query expansion. Now this is basically this goes hand in hand with equivalence classing, although you can think of query expansion also. I mean, you can implement it either way, but we are discussing a set of techniques, right? So we're not talking about one single way to do normalization. I'm telling you a set of techniques, and you will need to decide based on the trade-offs which of them you want to use. So let's look at something called stemming, which is an alternative to lemmatization. Lemmatization requires a fairly sophisticated linguistic analysis of the text because you need to convert every word to its root form in the dictionary, which you can't unless you understand the language properly. And this linguistic module is also pretty sophisticated, that the lemmatization module has to be extremely sophisticated. Stemming is a more crude form of normalization, where again you try to convert terms to their root forms, and again it's language dependent, but the technique used is a little simpler. It's more crude relative to lemmatization. What you do in stemming is you take all, in order to create an equivalence class, you look at all the variants of uh, a particular root form, and then you chop off some characters from the end of each variant to generate that root form. So automate, automatic, automation all get reduced to this term automat. Now note that automat is not a valid word in the dictionary, right? So unlike lemmatization, stemming does not really create valid words when when you create the final term. But it just chops off letters from the end so that variants, because many times the variants of words differ in the characters at the end. So if you want to map all of them to the same term, one way to do that is to chop off characters from the end so that whatever comes before that, whatever is preserved is basically the same for all those words. So here's an example. Uh, Again, this is a sequence of tokens, and after stemming, you can see that example has become converted to example without the E. Compressed gets converted into compress when you chop off this ed. Compression also, you chop off this ion and it gets converted into compress. In R you chop off this E, it gets converted to R. Accepted, you chop off ed. In equivalent you chop off ent, and so on. So this is called stemming. And there are multiple stemmers. There are all kinds of stemming algorithms that are available. One of the most popular ones is called Porter's algorithm, which is developed by Martin Porter in the UK, and it's used for English. So again, stemming algorithms are language dependent. So this particular algorithm is used for stemming English documents, and it's at least as good as the other stemming options for English. So you don't have to exactly know the algorithm in great detail because it's a huge case analysis kind of algorithm. But let me just give you a sample of the kind of things that it does. The algorithm has 5 phases of reductions. Okay, so what does a phase consist of? A phase consists of a sequence of production rules. So have you done a course on theory of computation, automata theory? You might have done discussed production rules there, right? Rules of where you take a string that appears on the left hand side and you replace it by a string that appears on the right hand side in the grammar. So this is kind of like that. You in each phase of Porter's algorithm, you you have so the algorithm uses a bunch of rules, right? So this is a bunch of rules, and for every word, for every token that you take, you're going to see whether the suffix, whether there is any of these, whether any of these is a suffix of that token. So there's a lot
I
of
can hear
disturbance.
some noise, so a lot of disturbance.
Yeah. Where is it coming from? Viswajit? Yeah. Okay. Okay. Yeah,
Yeah, now
it's
it's
fine.
okay, sir.
Okay.
Yeah.
So in each phase of the algorithm, you have a bunch of rules, okay? And the rules for phase one may be different from the rules for phase two. Okay, so in phase one, for example, you will take every token and you'll do a longest suffix match between your token and all these strings on the left hand side of these rules. So for example, if you take a word like kereses, so SSES matches with this SSES. So what will happen is this SSES will get replaced with SS, and so this will become keres. And if it's something like keres itself, well, there's no suffix here that matches any of these terms, any of these strings, and so this will remain as it is. So the different forms of this word have gotten mapped to the same term. So this is what happens in a particular phase of reduction. Now once this is done, you will have phase 2. Right? In phase 2 there'll be another set of rules. There may be a rule saying, well, SS, take SS and map it to S. In which case after phase 2 this will become CARES. I mean, I'm not saying this is an actual rule, but there'll be a different set of rules over here which you will apply on the output of phase 1. Then you'll take the output of phase 2 and apply another set of rules for phase 3, and then another set of rules for phase 4, and another set of rules for phase 5, and what comes out of phase 5 will be the terms. So a single term at the beginning will go through potentially 5 steps of transformation because before it ends up in the dictionary. So the phases are applied sequentially. Each phase consists of a set of rules of the form we just saw, and the convention is that if there are multiple rules, you're going to choose that particular rule which applies to the longest suffix of your token. Now some of the rules are also sensitive to the length of the words. So for example, there could be a rule like this. Uh, if there is a word that ends with EMENT such that whatever comes before the EMENT has a length of has a length more than 1, then replace this with then just delete this EMENT. So this is a blank string, that means this is getting deleted. So replacement, for example, is a word where you have EMENT and what comes here has a length greater than 1. So this will get converted into REPLAC. But cement won't get converted because if you take out the EMENT, C has a length equal to 1, whereas this says that the length should be greater than 1. So if the length is not greater than 1, then the rule doesn't apply. So cement will remain as it is. And you can see why this is the case, right? Because if this particular, if what comes before the EMENT is pretty long, then there's a chance that this EMENT is sort of a variant form of a root word. And so it makes sense to just chop it off so that you hopefully get a section of the root word. But if it's just a single word, C, then, this is probably an entire word in itself. It's not the variant of a root word. And so you'll keep it as it is. Is this clear?
Yes, sir.
Okay. Now there are other stemmers apart from Porter's stemmer. For example, there is this single pass Lowen stemmer. Okay, it doesn't have 5 phases, it has a single phase, and it has about 250 rules. And again, it removes the longest suffix. And there are other examples of stemmers. So stemming is an alternative to lemmatization, and it's an easier, it requires a less sophisticated understanding of the language. It's a more crude way to convert words into their root form. Now the question is, are stemming and lemmatization helpful? It turns out that a full-blown morphological analysis, the word
Hello,
morphology stands for, hello,
sir. There was a problem with Skype.
okay,
So can you just repeat the thing?
what was the last thing you heard?
From the beginning of this slide, sir, probably.
Okay, so I was referring to other stemmers apart from Porter's stemmer, and one other example is the Lowen stemmer, which is a single pass stemmer. So it has a single phase. Instead of 5 phases, it has a single phase, and it again removes the longest suffix. And there are other examples of stemmers for English. Now the question is, to what extent does stemming or lemmatization help? It turns out that a full-fledged language analysis of words followed by in order to convert these words into a root form does not significantly improve the quality of your engine results. There are some benefits, but the benefits are not great for English. So here's an example where stemming or other forms of normalization may not actually help. If you look at words like operative, operational, and operating, these are variant forms of the same root word, something like operate. So if we do stemming, all these 3 words get converted into OPER. But we can see that in the process of converting these terms into the root form, so consider a phrase like operative dentistry. Okay, this is a particular technical term, or operations research, which is a field, operating systems. If these 3 words beginning with an O get converted into OPER, then consider a document like um, operating a database system. So by converting, well, this is an example where it won't um, make any difference, but here's another example, operating a dentistry business. So a document like this is going to match. So if the query is operative dentistry, which is a particular kind of dentistry, that's going to match this document also, because operating and operative map to the same term, OPER. Or is your dentistry business operational? If somebody asks this question in a document, is your dentistry business operational? That document will also match with operative dentistry. So what happens as a result of stemming is that even though your recall gets increased, why does your recall get increased? Because your documents that are going to be, the documents that are going to be returned to you are going to have variant forms of that word as well. So the recall will be high, but precision is harmed because there could be other spurious words which also get mapped to the same term. So precision gets harmed, recall gets helped for English, and the results are very mixed, so it's not clear that stemming and lemmatization decidedly help. But for other languages like Spanish, German and Finnish, it's been shown that stemming or lemmatization is definitely helpful. Now what's different about these languages? Well, these languages have a very rich morphological structure. So morphology refers to the structure of a particular word in a language. Morphology is the study of words, and in certain languages, the words have a very well-defined set of rules for generating the variant forms. English is a little messier example of a language, but if your language is very elegant in how it defines the variant forms of words, then you can use something like stemming and lemmatization in a much more beneficial way. But in English, it's the results are pretty mixed. So you can see that the various normalizations that we have discussed are language specific, and many times they may be application specific. If you're dealing only with, say, the health domain, then you could use certain ways of normalization which you wouldn't use for uh, English in general. Or if your audience is only medical professionals or lawyers, then you can use certain forms of normalization that you wouldn't use in the context of the web. And many times these modules for lemmatization, stemming, and so on are plugin modules which are added to the overall indexing process, as we saw in the pipeline. And these plugins could be both open source as well as commercial. Now, one thing that I mentioned a few slides ago was the fact that a single document or a single corpus set of documents could have words or documents from various languages, from multiple languages. We saw an example of a German sentence which mentioned MIT, the university, and there could be other German documents which refer to MIT, the German word. So in that case, your index will have a dictionary composed of words from multiple languages. Now, one way you can store words from multiple languages in your dictionary is by appending the name of the language with every term in the dictionary. Right? So for example, this particular term gets appended with .Japanese. MIT gets appended with .English, and MIT here gets appended with .German. This helps because if you have a German document, then, and if it has the word MIT in it, especially when it's not capitalized, you could specifically look up the postings list for this term, MIT.German, instead of collapsing this MIT and this MIT into a single postings list. You could keep them separate because they correspond to different languages. And you can use language detection techniques to generate these tokens by detecting which documents are written in what language. You can detect, you can add these terms associated with their language, and then you can take a query term, again map it to some language, and then look up those terms in that particular language, appended with the name of that language in the dictionary.